All right, welcome to the next talk, All Your Macs Are Belong to Us. Today I'm stoked to be co-presenting with two stellar security researchers. We have Cedric from Zoom, round of applause. And Jaron Bradley from Jamf. Jaron, come on. Don't be shy. All right, so today's talk is a story we wanted to share with you all, whose main character is a rather lovely bug that affected all recent versions of macOS. So in this talk, we will take you through various chapters that cover the discovery of the bug by the one and only Cedric. And then we'll also dig into the root cause of the bug. We'll then talk about exploitation in the wild and how Jaron was able to uncover attackers abusing this vulnerability as a zero-day to target Mac users. I'll then wrap this up by talking about some methods of detection and also reverse engineering Apple's patch. So now I'm going to hand this off to Cedric, who is going to talk about how he found the bug and its impact.
All right, good morning. Good morning, everyone. Cedric, super excited to be here and excited to even more excited to sort of talk through how I found the bug and what the impact was for everyday Mac users. But before we do that, I'm going to jump into some basics, kind of like a refresher for most of us of the core components of macOS security. We have prevention, detection, and removal at a very high level. From a prevention perspective, Gatekeeper is the main aspect, the main component of macOS that provides prevention. And to even step back further, Apple added something called file quarantine a while back, where files that are downloaded via web browsers or via AirDrop using Bluetooth and various other methods, they're appended this attribute called the quarantine attribute, the com.apple.quarantine attribute. And what Gatekeeper does is it inspects files for that attribute and it looks for certain file types. So things like Mako binaries, app bundles, installer packages. There's a certain group of file types that Gatekeeper inspects. So if the file matches those types and it has that com.apple.quarantine attribute, Gatekeeper steps in and performs its checks. And it does mainly two types of checks, one of them being validating that the file you're trying to run has been signed with a valid developer ID and has also been notarized, meaning it has been uploaded to Apple's notarization scanners that look for malicious software. And if it passes notarization, then a notarization staple is notarization ticket is stapled on to your the file you're trying to run. So it checks, and of course, if the user still has the option to right-click and open, if you want to run something that is not signed and is not notarized, you can right-click open and do that. From a detection perspective, XProtect is the main component of that aspect, where even though it is sort of a component of Gatekeeper, XProtect is where Apple sort of has its intel of real-world malware samples that it has seen. Different Yara signatures and detections are built into XProtect, and so those are updated periodically to macOS devices. And then, of course, you have the removal with mrt.app, which also sits with Apple Intel. From a red team perspective, which is what I do currently as Patrick mentioned at Zoom, and red teaming environments that are primarily macOS, from a red team perspective, Gatekeeper is really the biggest hurdle of these three. XProtect and MRT don't really come into play much for red teams usually, because we often will write our own stuff for red team exercises that we're running, whereas XProtect and MRT are based on more like real world samples that Apple has seen. Other core security controls, privacy protections, or TCC, transparency, consent, and control. And what Apple intended to do with that is to put the power in the hands of the user to determine what programs can access like sensitive places on macOS. So while all directories are not protected by privacy controls, some of the common ones that are protected are like the user's desktop, user's downloads folder, user's documents folder, etc. Again, every place is not protected, so the user's base home directory is not protected. So you think about all the files you might have there with sensitive information or credentials, like that's not protected. The base users SSH directory, AWS, Azure, where keys are stored, where you might be able to move laterally to like cloud environments, that stuff's not protected by TCC. The Evil Bit and Reggie did a talk this year at Black Hat 2021 on 20 plus ways. I think that number's actually gone up since then as they found other bypasses. So if you're really interested in looking at more bypasses, definitely check their Black Hat talk out. From a red team perspective, this information here is more like working around TCC as opposed to bypassing it, since there's still a lot of information that TCC or your privacy controls does not protect. And then, of course, you have app transport security. So from a red team perspective, if we're building an app bundle as part of our red team exercise, app transport security becomes a pain at times, because what ATS does is it's Apple's way of controlling what an application can communicate out to. So if you have, let's say you're building a red team app and you have a command and control server and you want your app to talk over HTTP, that's where app transport security comes in, because you have to go into info.plist file and you have to allow arbitrary loads, make entries to the info.plist file in order to allow that app to talk out over HTTP. If you're using SSL, app transport security actually prevents that app from talking to a server using a self-signed cert. So it actually has to be a valid SSL cert. So you can see just some examples of how, from a red team perspective, app transport security can be a pain as well. And so summarizing these controls, going back to the bug, that was sort of the motivating factor for me to find something, find some kind of bypass to allow us to have red team payloads with minimal hurdles possible. And that's sort of what led me to the research. And our common payloads up to this point were like Mako binaries, which are checked by Gatekeeper, but they're not remote friendly, meaning most of the time, like they're not going to be double clickable. Usually we'll use something else to pull down a Mako. You have your app bundles, which are checked by Gatekeeper. They are remote friendly, meaning you can double click them. But again, you got to deal with Gatekeeper. Same with installer packages and weaponized PDFs. However, I did know at the time that scripting languages were not checked by Gatekeeper. So things like Bash, Python, JXA, which is JavaScript for automation, which Cody Thomas actually brought to the forefront for a lot of researchers on the possibilities with that. Those types of languages were not checked by Gatekeeper, as well as like Microsoft Office macros, not checked by Gatekeeper, but Microsoft opts into the sandbox. So now you don't have access to all the functions on a disk. So you can see sort of the pros and cons with all of the different payload types, and why at the time I'm like, man, I don't really want to use any of these. I want something different that can bypass some of these controls. And that's what led to CVE 2021-30657 that I reported to Apple and worked with them to get fixed. In a nutshell, it's what we call subverting the bundle structure. So the basic bundle structure for app bundles on macOS is you have the name of the app, then inside of that you have a contents folder, then a macOS folder, and then at the bottom you have a Mako. And then the Mako binary is what is actually executed when you double click like an app to run it. It's just that the info.plist and resources file, all those other things within the bundle structure are just wrappers around it. So the thought process, came to me, like we looked at the other slide of how scripting languages are not checked by Gatekeeper. Well, what if we swap the Mako binary out with a script at the bottom of the directory structure, since that would make it double clickable, and in theory it would get around Gatekeeper. So that was the thought process I went down. Even found that years ago, developers were doing this technique to turn their shell scripts into executable, like double clickable shell scripts. They were using this exact technique. And so of course I ran it and used it as a stager to pull down really any other second stage payload and execute it, and found that it was working. Privately messaged Patrick, like, dude, you should check this out. He ran it and it's like, oh, it's beautiful. Like it works. And that's sort of what led to me reporting it immediately to Apple. Here's an example of one of the payloads. So you can see at the bottom of the bundle structure, real app is the shell script, and I matched the name of the bundle at the top, real app.app. And the shell script itself did two things. It pulled down an unsigned Mako, which I did just for demonstration purposes when I reported it to Apple, to show that like the second stage payload could be anything, because I was using curl to pull it down. And curl is not a pin that worrisome quarantine attribute to anything it pulls down. So of course you use curl and it pulled down the file, The unsigned Mako, it set the executable bit and it ran it backgrounded. And then the second section of it was just a fake pop-up to the user, like based on your red team social engineering pretext to convince them that, hey, this is an IT installed app. Thanks for installing it. Like no other actions are needed on your part. So that's just an example of like what the payload itself looked like very basic, very simple. And again, just to go through some of the benefits of this payload, it fully bypassed Gatekeeper, which was really the main objective at the time. And you can see on the right just examples of like OneDrive and then my fake app, just by copying the icon over to the fake app. It looks very convincing. And without a user kind of digging in and looking at file sizes and like, hey, says it's OneDrive, but it's kind of small, they probably wouldn't notice the difference if they're kind of moving about their day. Also, you can use it as a stager to download any second stage you want. And another thing I liked about it is even though it was an app bundle, I didn't have to worry about app transport security and all those info.plist entries and settings that you have to adjust. So Apple did respond in 5 days. They patched it in Big Sur 11.3 as well as Catalina. However, I will note that their patch was really more Gatekeeper flagging it. I thought what Apple was going to do was actually just invalidate this type of app altogether because it doesn't even have an info.plist built in, which you would expect in app bundles. But ironically, that is still treated as an app. So even today, this still can be useful from a red team perspective. You just have to social engineer the user to right-click open. But it's still a beneficial payload because you get around app transport security and some of the other nuisances when dealing with app bundles. You don't have to worry about sandbox, et cetera. So quickly discussing my experience reporting it with Apple. Big bug again. Researchers like Parick looked at it and said, hey, out of the stuff I've seen, this is probably the most significant bug for everyday users because of how easy it is to build something like this and how widespread it is in terms of the impact. And they reported to Apple before disclosing it publicly. They fixed it in 5 days. The content from their website says any device attacked via a user-installed app that gains access to sensitive data is $100,000. But you do notice that there's two little asterisks there, which I'm like, oh crap. So what does that mean? The asterisk here is Apple's definition of sensitive data, which they define as contacts, mail, messages, notes, photos, or location data, which from an individual user perspective, like somebody just buying Mac and using it at home, that kind of makes sense, right? But from an enterprise perspective, where Silicon Valley is using Macs across the enterprise, I don't care about any of that stuff. I'm going after SSH keys, I'm going after password files. So it was a shame when reporting it to Apple that I couldn't get them to agree with me that this payload that I reported to you all, worked with you all to fix, actually does access sensitive data. Instead, they stuck to their narrow definition, which allowed me to get a much smaller bounty payment of $5,000 as opposed to $100,000. And $5,000 for most bounty payments is pretty good, but it's just a principle that Apple just didn't really understand, at least in my opinion, the enterprise impact of what sensitive data means, like at the enterprise level. Yes, so hopefully Apple will change. If you're listening, please expand that definition and make it more relevant for enterprises. So now Parick's going to come and dig into the bowels of the vulnerability itself.
Yeah, man, awesome bug, Cedric. Super stoked. Feel really excited to talk about it today. So as Cedric noted, he reached out to me to both verify the bug and dig into the root cause. I mean, we were both rather stumped about how something fairly trivial could sidestep a myriad of foundational macOS security features. 100% reliable, logic bug, download, execute. Very powerful bug, as Cedric noted, really had the ability to impact a lot of Mac users. So I began by triaging the proof of concept that Cedric sent me. I said, okay, double check, yes, it's unsigned. Also, it's not notarized, and so that's strange. I also made sure that the quarantine attribute was set. The quarantine attribute, as Cedric talked about, is what triggers the gatekeeper, the file quarantine, and the notarization checks. So I thought maybe for some reason the quarantine attribute is not set. But as we can see on the slide, it was. So we have an unsigned application that can bypass file quarantine, notarization requirements, and gatekeeper. Strange. As Cedric mentioned, the interesting thing about this application that he crafted that was able to trivially bypass the security mechanisms was what I'll refer to as a bare-boned application, in the sense that it did not have an info.plist file. Info.plist file, as Cedric touched on, is a metadata file that contains information about the application. I thought it was always required by an application, apparently not. Also, and this will be important when we look into the root cause of the vulnerability, this application had a script at its main executable component. So again, we have a bare-boned application missing an info.plist file whose executable component is a script, not a standard Mach-O executable. So I ran the proof of concept on a fully patched macOS system, and instead of being blocked by the operating system as we would expect because it's unsigned and not notarized, it was allowed to execute. So obviously there was a flaw, a bug. I wanted to figure out exactly what the root cause, the underlying vulnerability was. Unfortunately, this was somewhat difficult because when a user, or someone like myself who's researching a flaw, double-clicks an application, there are a myriad of system components that behind the scenes come into play. No less than half a dozen user mode applications, system daemons, and even the kernel gets involved in parsing, processing the application, and ultimately launching this. So the question was, which one of these components was flawed? So instead of reverse engineering all of these, living in Maui, I like to spend some time surfing, not sitting in front of my computer all day, believe it or not. I said, okay, there's got to be a more efficient way to do this. So my approach was the following. I decided to run 3 different unsigned applications from the internet while monitoring log messages, and then the plan was to look for where the log messages diverged with the proof of concept application, which would hopefully at least point me in the right direction where the vulnerability lay. So the 3 applications we have, again, they're all unsigned, all from the internet. The first is a standard Mach-O executable application. And when we run it, as expected, it's blocked because it's unsigned and unnotarized. The second application was an application bundle that had an info.plist file, so a standard application, but its executable component was a script. Also, when we run this, as expected, it was blocked. The third one was then the proof of concept application from Cedric, which is this bare-boned application missing both the info.plist file and whose executable component is a script. And as we can see, this was allowed. So I first ran the standard Mach-O executable binary, which was blocked as expected. And as we can see in the log messages, 2 important things popped out. First, we can see that the daemon that's doing the analysis of the application is something called syspolicyd. As its name implies, it is what enforces policies. For example, whether an application from the internet should be blocked or denied. And ultimately, this is where the vulnerability lay. So this was good. This gave me a breadcrumb, said, hey, this is likely the component that has the flaw, the vulnerability in it. The other interesting thing we see is a log message that relates to a gatekeeper evaluation. And in this evaluation, in this log message, we can see 2 things. First, the evaluation scan result is a 0. We don't know what that means, but we'll see it's important. And then following this, there's a log message that says GK, gatekeeper eval, was allowed equals 0 or false, show prompt equals 1 or true. This is unsurprising. Gatekeeper is basically saying, GTFO, this is an unsigned application. I'm not going to allow it, and I'm going to show a prompt to the user. Then I ran the script-based application that still had the info.plist file, so the second app. And the log output was very similar, save for one difference. We can see at the top there is a log message that says script-based evaluation. So this shows us that there is at least an alternate code path that the operating system takes when processing script-based applications. But recall again, this second application was also blocked, so it's unsurprising that we see again the same log message showing that the gatekeeper scan result has determined this application should be blocked and a prompt should be shown. Finally, we have Cedric's proof of concept, the bare-bones script-based application, bash script with no info.plist file. We can see that script evaluation log message, so now we know we're going down that same code path. But interestingly enough, if we look at the GK evaluation result, there is a 2, not a 0. Also, there is no message about the application being disallowed and a prompt being shown, which is unsurprising because it was allowed with no prompt to the user. So, summary based on the log messages, if we run a Mach-O-based application or a script-based one that has an info.plist file, Gatekeeper will return an evaluation type of 0 and block the application. However, for the bare-bones script-based application, we get a GK evaluation result of 2, which for some reason allows the application to execute. So we have some breadcrumbs. We know syspolicy-d appears to be triggering the Gatekeeper evaluations, and we know now that for some reason it's evaluating our bare-bones script-based application to type 2, which again for some reason means it's allowed. So the question then becomes, what is evaluation type 2? Where is it set? Because this is likely going to point us exactly to the root cause of the vulnerability. So I started reverse engineering syspolicy-d. It's closed source, but pretty easy to disassemble. We have some decompilation on the slide. We can see there's a method called evaluate scan result. And we can see, based on the argument names, the 5th argument is the evaluation type. And we can see it checks explicitly if that type is 2. And if that type is 2, it calls a setAllowed method with a value of yes or true, and then just returns. And we can, again, confirm this in a debugger, seeing that allowed is set to yes and would prompt is set to no. So this is kind of confirming our logic that if an evaluation of type 2 is returned, we still don't know what that means, but if that occurs, the operating system will basically say, yeah, you're good, run, no prompt. Onwards. So now we want to know, where does this type 2 get set? So if we look at the stack trace, continue our reverse engineering, we find a method named determine gatekeeper evaluation. And I have the disassembly, the decompilation of that. We can see various if statements and control flow decisions that we can kind of step through and see what happens when we launch this script-based bare-boned application. The first check is user approved? It's not yet, right? We've just downloaded from the internet. So that returns no, so we step now into the next check. It then calls is script. Since we have a script-based application, this will evaluate to true, so then we step into the 3rd logic block. Note though, before the last check, they set the R15 register to the value 2, and that is ultimately what is returned. So they're hard-coding the return value. However, before they exit with this return value, they call a method isBundled. And if that is set to false, it's going to leave with an evaluation type set to 2. Interesting. So of course, now we want to figure out, what does isBundled mean, because this is why an evaluation type of 2 is returned, which ultimately allows the application to run. So if we look at the isBundled method, it turns out just to return the value of an instance variable. So that's not really that helpful. However, we now have a name of an instance variable, isBundled, and we can look elsewhere in the disassembly of syspolicy-d to see ultimately where this is set. We can see that on the slide. There's a method named evaluate code from user, and as we can see, it calls an unnamed subroutine, and based on the return value of that subroutine, updates the isBundled variable. So now we need to dig into that unnamed subroutine to figure out why it's deciding our application is not a bundle. Well, if we look at the disassembly, the decompilation, it's very obvious. It's basically checking if a script-based application has an info.plist file. And if it doesn't, it says, no, this is not a bundle, so returns false, which means that type 2 will get propagated back into the policy subsystem, which means the application will then be allowed. Of course, recall our application does not have an info.plist file, which triggers the isBundled algorithm to essentially fail and misclassify our application. And again, we can confirm this in a debugger if we print out the value of the isBundled instance variable after this function has returned. We can see the system, as expected, has incorrectly classified this bare-bones script-based application as not a bundle. So in summary, if this happens, the operating system allows the application. So again, if you don't have an info.plist file and your application has a script for its main executable component, that would trigger the flaw in the bundle classification logic, which neatly sidesteps, as we saw, gatekeeper, notarization, and file quarantine. So next up, I'm going to hand this off to Jaron, who's going to talk about some interesting research that ultimately uncovered this being exploited in the wild as a 0-day.
Cool. Everybody follow that? All right, so yeah, Cedric talked to you a bit about like discovering the bug. Patrick talked to you about how he, kind of dug into it, and discovered why the bug worked. So I'm going to talk through a bit about how we uncovered this being used in the wild, which was definitely pretty cool. So first off, Patrick obviously, kind of messaged out to me and asked if, Jamf Protect was capable of seeing when a script was used as the main executable inside of an app bundle. And I said, sure, yeah, we should be able to do that. But I didn't have all the details. Patrick passed me some of the details, and we played with it a bit. Decided, yeah, there's something weird going on here. So, so basically, the way we're able to put a detection in place with Jamf Protect, obviously with a zero-day type of approach, we want to come with a more behavioral-based detection style for this rather than some type of static-based detection. So what we want to do with Jamf Protect is find a way to pick up on the behavior of this being done. Given all the details we knew, it wasn't too tough, but just to understand a bit about how we're able to put detections in place, basically Jamf looks for a number of behaviors occurring, for instance, processes being created. When that process is created, we take a look at the command line, we take a look at the path of to the file. We're able to see the hashes, things like that. Files as well, we're able to see files being modified, created, deleted, which processes are doing those activities, as well as, many different other types of behaviors. Downloads occurring, basically we get a visualization into what's happening with these by standardizing these events to some type of JSON, and then we run them through a detections engine. When any of these occurs, we can then perform a number of checks to decide if what we saw we think was legitimate or if we think it was shady in some manner, and then ultimately put that in front of the analyst and leave it up to them to decide. So from a detections perspective on this one, we are going to use a process create. We know that a script running is kind of what initially triggers when we want to perform some checks. So a process being created, in this case, we dealt with a proof of concept script. So when that process runs, we check to verify that this program that just ran is a script. Obviously, that is a requirement in order for this entire exploit to work. So first we verify that. Once we've verified that it's a script, if it truly is, we go on to perform some more checks. And the biggest, or one of the next required checks being that this is an actual app bundle. There's a couple different ways to determine if you're running in an app bundle or if a script that just ran is part of an app bundle. I believe there's some libraries you can use, or you can actually just look, 2 directories up in the path to determine if it's a .app folder. And so that's one of the things we do next, and this is more for false positive reduction. We want to verify that the parent of this proof of concept script that is part of an app was run by launchd, has a parent of launchd. So for instance, we don't care if this script was run in a terminal. That's not part of this exploit, right? This is what's required here is a user double-clicking on the application. And when you double-click on an application, launchd is going to be the parent process of your new executed script in this case. Another thing we want to check is, as Patrick mentioned, the first time you run this script, it is being checked by Gatekeeper. It's not something that just completely skips past Gatekeeper. It's something that Gatekeeper looks at and then approves. So we also want to verify that this script is being checked by Gatekeeper. There's a couple different ways to do that as well. I believe Patrick will talk on some in future slides. One way to do that is to use, again, you can use some Apple libraries, or if you're looking for a script that's being executed from a DMG, which will tend to be the case with this particular exploit, or maybe a zip file, you are checking the app translocation directory, or that this script is being executed from an app translocation directory somewhere up its path. So we take a look at that as well and ensure that this is currently being analyzed by Gatekeeper. Finally, because we know that, again, there's more ways to reduce false positives, And the more false positives you reduce, the less time you waste when you're actually looking at, detections that have hit. We check to ensure that the script name matches the application name perfectly. This is a requirement in order for the bypass to work. So just, being as tight as we can on the rules and doing that. The other, I believe you also cannot have an extension on the script itself in order for the bypass to work, unless you've also included that extension inside of your application name, which just nobody's going to do that. But you could, and we're prepared for it. So sure enough, we released this detection, and I think it was all of 2 days later, we saw this detection hit out in the wild. I know it's probably a little hard to read, but what we have here is we see that bash is the running process, or the path to the process that was executed. A application named 1302. I don't know how many of you develop applications, but probably not many of you that name your app entirely in numbers. That doesn't really mean anything to users. So this instantly looks pretty shady to us. You can see in the process arguments, it's running out of the app translocation directory, meaning we know that Gatekeeper's kind of taking a peek at this, or has taken a peek at it. And finally, the parent process is that of 1, or launch D. So this matches everything that we are looking for, hitting on an M1 MacBook Pro. So I kind of reached out to Patrick. I still didn't have entirely all the details of what was going on, but I kind of made the assumption maybe Cedric had stumbled upon this because he'd found malware using it in the wild. And I was wrong. Patrick responded back, and he said no, someone found this just by playing with some different app bundle style stuff and realized that a script would let you through. And I thought, oh, okay, well, there's malware using it. I guess you know that now. And obviously, Patrick asked for a sample. And if you know Patrick, about the worst thing you can tell him is that you can't have the sample and you can't blog about it. So I was obviously joking, for those of you that know, because Patrick definitely did release a blog about this, like about a week later or whatever. So I passed the sample off to Patrick. We looked at it ourselves, and we kind of just tried to get an idea of what this actually was. So after we opened it, for those of you that have dealt with Schlayer before, Schlayer is actually, it's very obvious when you're dealing with Schlayer because it's generally a very short script of some type doing some very shady things. It's not overly complex to analyze because of how straightforward it kind of is, or how little code is actually in there. So after we verified it with Schlayer, we kind of did some comparisons around here's what the old Schlayer kind of looked like, and here's what the Schlayer with the 0-day built into it looked like. So on the left, this is what the users presented with in the original variant. Schlayer would install generally by getting you to download, Flash Player, just like we see so much adware with these days, Schlayer being one of the biggest offenders for sure. But the old Schlayer would literally walk you through bypassing Gatekeeper, and this seems ridiculous, but it works. Schlayer is incredibly successful, and we see these installs all the time. So the old version of Schlayer says, please right-click this install PKG, which is not actually a PKG, it's just a bash script. And it says click open, and users will do that. They'll see the instructions built right into the DMG, right-click it, and click open, and this bypasses Gatekeeper altogether. The new 0-day variant, this is the picture on the right that you're looking at, and it's just double-click to install. You double-click it, nothing happens, the icon blinks, and then it's game over. So, and then the user closes it, thinks nothing of it, and that's that. So. We can tell by looking at the layouts of both variants that, and this is where we kind of knew Schlayer wasn't doing this on accident, because the authors had literally taken kind of the old version of it and just taken the same payloads, which I'll get into in a second, and just put them in the new format required in order to bypass this. Remember, this wasn't public news. We assume that the authors of Schlayer found this on their own and implemented it into their malware. So on the left, you see install.command, and then you see an installer, which is a soft link to install.command. So that installer is that kind of PKG icon that you see when it gets double-clicked. It's a soft link that just runs a script. When it gets right-clicked and then you click open, it just runs a script. On the right side, we see that we have install now leads to 1302.app as a soft link. 1302.app is the app bundle layout that we expect, where 1302 itself down there at the bottom is the bash script that is Schlayer. So it now matches the layout in order to abuse this bypass. From the payloads, on the left side, you're looking at the original variant payload without the 0-day. On the right side, you're looking at the variant payload with the 0-day. I'm next to positive. We saw the 0-day variant payload in non-0-day variants as well. I couldn't dig that up or find where that existed, but I'm almost positive we saw it. But in the on the left, the original variant payload, the only difference we really see here is the attacker would include the zip file as a resource fork on the file. So this is kind of your alternate data stream of the Mac OS world. If you want to include an image on your script, you usually attach that image as the resource fork. But in this case, the authors of Schlayer would attach a encrypted zip file as the resource fork. They then pull that, they go to a specific offset inside of that resource fork, and they pull out the zip file that is in there, they decrypt it, add execute permissions, run it, and then kill the terminal. It runs in a matter of, a couple milliseconds, and the terminal's out of your way. You almost know nothing happened. So on the right side, in the 0-day variant, very, very similar, but instead the attackers, instead of using a resource fork, they include the encrypted zip file at the bottom of the script itself. So you see on line 3, they'll use the tail command to go to the offset of the script where the zip file is held, pull the zip file out, decrypt it, and then run what is the adware that it's looking to install. Getting a bit lazy. So what you're looking at here is virus totals entry around the time that we found this 0-day in the wild. So you'll notice that many vendors were picking up this 0-day, just nobody knew there was a 0-day in there. So that kind of tells you the authors of Schlayer maybe even gives you a little insight into their success rate, right? Generally, when you find a 0-day, you don't just burn that 0-day, you kind of rewrite the malware, you try and make it so nobody's gonna pick up on it. But in this case, we see 10 vendors picking up on this malware already just through static scanning of some manner. So I think that gives you a little insight into how successful the authors are with this. Just, dropping 0 days, not modifying anything. If it gets caught, it gets caught, whatever. People will still right-click and run our payload anyway. So just kind of an interesting little fact there. XProtect was updated shortly after. Cedric mentioned XProtect in the rules, how it's kind of Apple's built-in, virus scanner. And you can see here the different strings that they're looking for to determine when they see Schlayer. XProtect, these rules are available to look at for anybody that's sitting on the system. A lot of people know that, attackers know that. But in this case, we see that Apple kind of released this new rule that looks for the different strings and kind of different strings that you see inside of the Schlayer script itself. So when Schlayer does run, instead you'll see this package may be damaged. You can't run it instead of it successfully running. So this was released pretty quickly after everything kind of came to light, which is good on Apple. However, 3 days later, we found a new sample that had added to the fun zip command. They had added double spacing in between each of them. And this required the defeation of the XProtect rule that was just released. So, and again, 3 days later. So this tells you a bit about how agile and how ready the developers of Schlayer are. You can imagine that's like well within, unit test time, where they're just testing this malware every day, seeing if it runs, seeing if it works. When it gets blocked, they go in, they add extra spaces. So that's, I think, just a bit telling about how, how demanding these authors are and how often they're gonna keep doing this because their success rate is just so high. So I'll now pass it back to Patrick, who will talk about some additional protections and detections.
Now we're even more professional. All right, so we have a zero-day vulnerability that unfortunately is being exploited in the wild at this time. And so, as Cedric mentioned, he had reported this vulnerability to Apple. But in the meantime, it seemed reasonable to develop and deploy a protection mechanism to protect Mac users. So I thought about this for a minute, and I said, can we just detect and block the execution of any downloaded code that is not notarized? This is essentially what Apple is trying to do, but due to this bug in their policy subsystem, it's not working. But maybe we can get it right. So in 4 simple steps, the idea I had was to detect any new process launches, and then check if that item was from the internet and launched by the user. So if someone's locally opening Calculator or Pages, like, I'm gonna ignore all that. A developer running some script, that's fine. But if it's something from the internet that the user has double-clicked and launched, I wanna validate and check if it's notarized, step 3. And ultimately, if it's not, I'm just gonna block it or alert the user that, hey, what they're about to launch is unnotarized. So now we're gonna walk through each of these steps to describe how I approached this. Again, with the goal of blocking unnotarized code from the internet. So using Apple's new endpoint security framework, we can very easily monitor for new process events. Kudos to Apple for releasing this. It's a great framework that third-party security tools can leverage for a variety of events, such as new process launches. So there's a snippet of code on the slide. There's more information in the blog post that I posted at the bottom. But the idea is you basically create a new endpoint security client and you tell it what events you are interested in here. Here we're only interested in one, which is the process exec event. However, it's the auth exec event, which that tells the operating system, hey, when a new process is launched, call my callback and wait till I tell you if I'm going to confirm or deny the process. So again, a very powerful callback mechanism that Apple affords to us via the endpoint security framework. So now we're getting callbacks from the operating system. Every time a new process is launched, the system has essentially allowed the process to almost launch, then called our callback and says, what do you want to do? Are you going to allow this process or are you going to block it? So the next thing we want to do is determine if this application is from the internet. Now there's a variety of ways. Perhaps you could check the quarantine attribute, but that gets a little complicated because that's not always cleared, even if the user approves it, et cetera, et cetera. Better way is to simply look for the status of the application, specifically its app translocation status. Now, when a user downloads an application from the internet and double-clicks it, what Apple does behind the scenes is something called translocation. They basically copy it to a randomized read-only mount and execute it from there. This is to mitigate against a vulnerability I talked at a few years ago at DEF CON called dilib hijacking. So what we can do is we can use some private APIs to query the path of the process that is about to get launched to see that if it has been translocated. If it's been translocated, this means that the operating system has determined it's from the internet and that the user has double-clicked it to run, which is exactly the type of applications we are interested in. Step 3 now, we need to check to see if this has been notarized or not, because obviously if the application has been notarized, we're going to allow it. There are public APIs you can call to check the status, the code signing status of an application or a file, including whether or not it has been notarized. So we make this call, and this returns to us a flag that will be set to yes or no based on the notarization status of the item. So what we can do is we can combine this all into one component. I added it to block, which is one of the free open source utilities from Objective-C. And now you can see when we run the proof of concept application, even on a fully patched system, which was still vulnerable, either the proof of concept or the Schleyer variant that Jamf and Jaron detected exploiting this vulnerability in the wild, we can see that block very easily detects that it is an item from the internet that is not notarized, and therefore will block it pending user approval. As I mentioned, this is open source, so you can hop onto GitHub if you're interested in diving more into the specifics of this implementation. Now I want to end the talk by talking about Apple's patch. Eventually, they did get around patching it, so kudos to them. The not-so-secret secret is a lot of times Apple's patches are subpar. I would say about half the CVEs I have credited to me are simply by bypassing Apple's patches. So it's always a really good idea to validate the patch, hold them accountable, maybe get a free CVE out of this. In this case, I was really interested to see, had we uncovered the correct root cause of the vulnerability. I was pretty sure, but it's often good to look at the patch to confirm if you were right. And also to see, was the patch comprehensive? So what I did, I downloaded the patch version of syspolicy-d, and since recall that we basically thought we had found the flaw, that unnamed subroutine that was misclassifying the items based as being a bundle or not, I decided to start there. And so I diffed those two binaries by simply looking at the code size and the number of blocks that had been added. And on the one side of the slide, we can see the unpatched version. On the other side, we can see the patched version. And we can see two things happen. The size has increased, which indicates new code, and the number of blocks, which are normally conditional control blocks, has almost increased by about 50%, which is indicative of new checks being added to a function. So this confirms that Apple did patch that unnamed subroutine that had misclassified the proof of concept application as not being a bundle when in reality it should. So now let's look at the fixes that they added to the patch. And so we can do this again by reverse engineering the patch version of the unnamed subroutine in the syspolicy daemon. The first check we see they now added is, does the item's path extension end in application, specifically app? This makes a lot of sense because in order for an application to be launched when the user double-clicks it, it has to end in .app. This is kind of the heuristic that Finder uses. You can test this, create a blank folder on your desktop, name it .app, double-click it, and Finder will attempt to launch it as an application. So we can see based on the decompilation, they basically get the path extension and check if it ends in .app. If it does, they say, we don't care about anything else. You are now a bundle. That's awesome. They also check if the item has the content / macOS directory structure. This is required for any application, but more importantly for other bundles as well, perhaps dylibs or other frameworks. So again, looking at the disassembly and the decompilation at the bottom of the slide, we can see they build the path to content / macOS and then simply check if it exists. If it does, again, they abort early from the algorithm with a yes saying this item is indeed bundled. So here's a summary of the patch, the addition of those two checks I just talked about. First, does it end in .app, or does it contain content / macOS? And this is actually sufficient to correctly now classify both the proof of concept and the Schleyer variant that was exploiting this as a 0-day as being a bundle, which would then trigger the rest of the gatekeeper checks, ultimately resulting in an evaluation type now of 0 instead of 2, which will mean the application will be blocked, as it should, because it's unsigned and non-notarized, and a prompt being shown to the user. So let's now wrap this up. Some conclusions, some takeaways. So we talked about the vulnerability that Cedric discovered. Again, a beautiful bug, affected all recent versions of macOS. A lovely logic bug, meaning it was 100% efficient. We talked about the root cause analysis. We showed how you can use the logging subsystem to gain insight into the operating system, and also how that ultimately pinpointed, or at least pointed us in the right direction to look at syspolicy-d. We talked about reverse engineering that, how Jaron and Jamf were able to discover this being exploited independently in the wild as a 0-day, and then talked about some ideas for protections and mitigations, and also reverse engineered Apple's patch. Another main takeaway that I think is really important to note is macOS still has a lot of shallow bugs. Again, a wonderful bug Cedric found, but it wasn't through like incredibly complex fuzzing. I mean, it was deep within the subsystem, but it was a pretty shallow flaw, and a logic flaw nonetheless. I mean, obviously this code has never been audited by Apple or looked at by adversaries until now, which is kind of surprising. It's 2021. You think the core policy subsystem would be a little hardened. So that's just kind of an interesting takeaway. Also, I hope that some of the topics we talked about in this presentation give you the foundations to go off and do your splunking, your own macOS reverse engineering. So that is a wrap. There's some resources there. I think we're about out of time. So if there's any questions, hop on the Discord channel, and we'll answer them there. Obviously, Jaron, myself, and Cedric will be around for the rest of the conference, so feel free to approach us if you want to dive into this more. That's a wrap.